Alright, what is up my homies? Welcome to Brainmelt University. Today we're going to be talking about Internet Protocol version 6, what it is, how it works, and why we use it. When we developed IP version 4, we didn't really think about future-proofing it. The people who worked with IP version 4 and its development figured that the only people who would ever really be using the Internet Protocol were going to be large organizations, governments, universities, that sort of thing. They never really imagined a state where every single individual has a computer in their pocket. The number of IP addressing for IP version 4 is around 4.2 billion. They figured 4.2 billion was more than enough for everyone on the planet. But now we know different. We know that every human on average is going to need at least 5 IP addresses within the next 50 years. So we needed to come up with a new solution fast. We have stopgap measures with IP version 4, such as the use of private IP addressing and the use of network address translation. But for IP version 6, they really wanted to future-proof it, which is why when they were deciding to upgrade from a 32-bit value, giving you 2 to the 32nd power number of solutions, they decided to go with a 128-bit value that gives you 2 to the 128th power. So that's around 34 undecillion. That's 34 with 37 zeros after it. It's a big ass number. We'll probably never hit it, at least within our own lifetimes, unless nanotechnology just really takes off here. So your typical IP version 4 address has 3 components. The first component is called the global prefix. Your global prefix is the first 48 bits of your IP version 6 address. The global prefix is what helps decide what type of IP version 6 address it is. The next 16 bits are the subnet address. So we'll talk about subnetting in another video when we compare classful versus classless networking. The 64 bits that follow are what's called the interface identifier, or interface ID. The interface ID is just the unique identification of that device on the internet. Because of the sheer number of addressing, we don't really have a version of NAT for IP version 6. There are protocols that are designed to translate IP version 4 to 6 and back, but these aren't really true NAT. So when you see something like NAT 6 to 4 or NAT 64, these are really just trying to get devices that don't understand IP version 6 to take an IP version 6 address. IP version 6 is expressed in hexadecimal digits rather than decimal or binary. This allows us to cram a lot more numbers into a lot shorter space. IP version 6 also lets you use certain shorthand in order to not have to write out the full address, because even with hexadecimal, these are still quite long to have to write out longhand. One of the rules that we have for writing shorthand is that leading zeros can be eliminated. If we have a hextet, or collection of 16 bits, that is represented by the numbers 0010. We can actually eliminate the leading zeros, or the first 2 hexadecimal characters, out of there. So then that way we only have to write 10 and the computer can still figure it out. Another rule is that you can actually eliminate an entire hextet or multiple continuous hextets of all zeros. So if you have a hextet that is 0000, you can write that as just double colon. If you have 2 completely empty hextets, you can encompass both of them into a single double colon. Now there is a limitation, and that you do need to only use the double colon rule once. So if you have an IP version 6 address that has 2 different collections of all 0 hextets, you can use the double colon in one area, and then in the other you can simply write as colon 0 colon, and the computer still realizes that that is all zeros. The reason it does this is it needs to be able to reassemble the IP version 6 address whether you don't want to write it out longhand or not. Just like with IP version 4, we have reserved address ranges for IP version 6. One of these reserved ranges is the 2000/3 range. So the 2000/3 range means that the first 3 bits in an IP version 6 address needs to be 001. This range of IP version 6 addresses is for what's called globally unique addresses, GUAs, or GUAs. Don't call them GUAs. These GUA addresses are the equivalent of a public IP version 4. You just get to go about your day and enjoy your life. So because these are a /3, this means that the first 3 binary bits always have to be the same. So if this is 2000/3, that means that the first 3 bits, 001, can be preceded by everything from all zeros to all ones in binary. So that means that our range of GUA addresses is 2000 to 3FFF. The next range of IPv6 addresses that we have reserved are addresses that start with the characters FC/7. So if we look at FC/7, it looks like this. If we are not allowed to change those first 7 bits, then our range is FC00 through FDFF. This range is for what are called unique local addresses, or EULA addresses. EULA addresses are the IPv6 equivalent of a private IPv4 address. You can use these to route inside your organization all day long, but you can never use them to access the internet. EULA addresses, because there is no version of NAT for IPv6, are more limited than your IPv4 addresses. But if you're with an organization that is just trying to dip your foot in the water and trying to utilize IPv6 as a proof of concept, then ULA addresses are a nice option because you don't have to get a prefix given to you by your internet service provider or by IANA. Our next range is the FE80/10 range. The FE80/10 is reserved for link local addresses. Link local addresses are the IPv6 equivalent of the IPv4 APIPA address. In fact, some textbooks refer to both of these as link local addresses. For our purposes, we generally refer to the IPv4 as the automatic private IP address, APIPA, and we usually refer to the IPv6 as link local just as a way of distinguishing between which protocol we're discussing. Finally, we have multicast addresses. So multicast addresses in IPv6 work exactly the same way as they do in IPv4. These are just addresses that multiple devices on a network might be doing a similar job. So for instance, if you have multiple routers on a network that are all operating with OSPF for its routing protocol, they're all going to be listening for a specific set of multicast addresses. With IPv6, we just use an IPv6 multicast address instead of an IPv4 address. Your multicast addresses for IPv6 are reserved by the leading hextet FF00/8. If your first 2 characters in an IPv6 address are FF, odds are pretty good it's going to be a multicast address. Most of the ones that link directly to an IPv4 equivalent are FF02 addresses. So for instance, using my OSPF example, if a IPv4 router is using OSPF, it is specifically listening for traffic at 224.0.0.5 and 224.0.0.6. With IPv6, it would be listening for FF02::5 or FF02::6. So they pretty much are trying to mirror these IPv4 as much as possible and keep them short so you don't have to write out an entire group of IPv6 addresses. With IPv6, we do have a more simplified way of identifying between the network component, or in this case global prefix and subnet component, and the interface identifier or host portion of your address, like we do with IPv4. So where IPv4 uses something called a subnet mask, which is another 32-bit value that shows which bits belong to the network and which belong to the host, with IPv6, we use CIDR notation to just come out and say how many of these bits are being used for network and how many are being used for host. In most cases, you're going to be dealing with a /64, meaning the first half is for network, your global prefix plus your subnet, and the second half is all for your interface identifier. You can play beyond this, but you start to run into a few problems unless you're doing everything with static IP addressing. But this does give you a chance to really play around with IPv6 in the same way that we treat subnetting with IPv4. So there you have it, guys. There is your IPv6 reserved address ranges, how they are built and what they look like, how we use them. It's pretty much the same as IPv4, just newer and with way more addresses to get to play with. Feel free to like, subscribe, hit the notification bell. I'm trying to get new videos up every week. I had a problem with my recording software, so I kind of rage quit after recording 3 videos and then finding out that none of them had audio. So I'm back at it. We're trying to get this ball rolling again. My hope is to not only get 1 video up this week and also get caught up again. My next video should hopefully be on classful versus classless networking. We'll catch you later right back here at Brainmelt University.